When is the testing?
When we finish chapter 3. We will discuss it, we will review, and then we'll schedule it. We have to finish chapter 3 first. Okay, so I'm sorry,
21
205, problem 21. 205, 21. Okay, 21. Okay. So this is y equals x squared plus 1 over x squared minus 1 to the third power. So we're asked to differentiate this function, find the derivative. So this is like a function raised to a power. So y prime will be 3 multiplied by x squared plus 1 over x squared minus 1 squared times the inner function prime.
You use the quotient?
Yes, I have to.
Okay.
Yes.
2x.
So the top function prime is 2x times the denominator minus the top times the denominator prime over the denominator squared. Is this okay? So always remember, that's why we cover this in pre-calculus a lot, because simplifying by factoring is what needs to be done now. If you start distributing, you may have difficulties. Not on this particular problem because it's not that difficult, but in general. So I will factor out 2x. 2x is the common factor in both. So 2x times 3 in front is 6x. Bless you. X squared plus 1 over x squared minus 1 to the third. So now the top is x squared minus 1 minus x squared plus 1. Yes, they go, I'm sorry.
Why is it 230?
The minus here. That's my error. Say it again.
Why was x squared plus 1 to the third?
That's squared. The first parentheses.
Yeah, oh yeah, of course. Of course. No, I just didn't pay attention. I was looking at something else. Sorry about that. So this is minus here. Thank you. Of course. I have to copy what I see, what I have. So now the numerator is negative 2. Multiplied by 6x is negative 12x. And now I can do this. Not necessary, but we can do this. This is what I would have asked you to do anyway in chapter 4.
Raise left.
Is it okay?
How did you think about the
Where do I go back? Which step?
Where do you get negative 12x from? I get where the x squared plus 1 squared and the denominator comes from.
Negative 1 minus 1 is negative 2. Multiplied by 6x is negative 12x. If you separate the top and the bottom, you have x squared plus 1 squared, and x squared minus 1 squared. With these two will be 4. So that is the best shape of the final answer. And you'll see in chapter 4 why. I don't know how they presented it, what they did. What is their answer? But this is the best answer. How is this? Other questions? Anything else that you worked on? Anything else that you would like to go back to?
53 on 216?
53 on 216. 53 on 216. 53. I thought we did this in class, but maybe not. I may be wrong. Okay. That's okay. We can do it again if I don't really remember, so G prime first and second. So I have to use the product rule. We did? This is what I thought, but so that's okay. So this prime is 1 over 2 the square root of 1 minus x squared times negative 2x times arc cosine x. So far so good? Okay, plus, because it's a product rule, I copy the first one and differentiate the second one. The derivative of arc cosine is negative 1 over the square root of 1 minus x squared. So now I'm trying to simplify, or maybe not. I have to simplify these two. I can simplify the denominators here, but we prefer keeping it as a fraction form. And I see that the denominators are the same. Both expressions are negative, so I put negative in front. I write the square root of 1 minus x squared. And then the top is x arc cosine x, and plus the square root of 1 minus x squared. Is this okay?
That's it.
That's it. You cannot do anything else. Anything else here? Is this clear? Any questions? Is there anything else that we worked on and we need help with?
Could we do 19 on 248?
19 on 248, 248. Number 19.
I suck with triangles.
The altitude of a triangle is increasing at a rate of, okay. It's increasing at a rate of 1 centimeter per minute. What does this represent? Good. While the area of the triangle is increasing at a rate of 2 centimeters squared per minute.
What did you say?
While the area of the triangle is increasing at a rate of 2 centimeters squared per minute.
dA over dt.
Perfect. At what rate is the base of the triangle changing? When the altitude is 10 and the area is 100. At what rate is the base of the triangle changing? When the altitude is 10 and the area 100.
dB.
Should we read the problem one more time? Very good. The altitude of a triangle is increasing at a rate of 1 centimeter per minute, while the area is increasing at a rate of 2 centimeters squared per minute. At what rate is the base of the triangle changing when, and you know that when, that part is not even on our minds yet, when blah, blah, blah happens. Where is the starting point? Good. So I have to start with the area because the area will include the height and the base. What is the formula?
Half base times height.
Very good. Or you can write it as Reed said, as 1/2 base times height. Same thing. You can write it as 0.5 times base times height. They're all the same. Perfect. Is this my first page? Oh, yes, this is my first page. Okay, next. Next step. Good. I differentiate the left-hand side. I differentiate the right-hand side. The right-hand side I get,
2.
dA over dy.
of course, over the dt
Oh, dt, yeah.
equals
1/2 So it's gonna
very good
times
plus
b times BH over DT.
Perfect. Awesome. There are 3 related rates here, one for A, one for B, and one for H. So now I look at what I'm asked to find, and I know exactly which one is the variable. Which one is the variable from everything we see here? Yes, right here. Correct. So then I will distribute 1/2 or just multiply both sides by 2 to get rid of it. That will be the best. And then I will be moving this term to the other side and dividing everything by h. So first let's multiply everything by 2. So 2 dA over dt equals h dB over dt plus b dH over dt. I will move this term and divide everything by h. So dB over dt is this term, 2 times dA over dt minus b dH over dt, when the height is 10 and the area is 100. So let's see what we have and let's see what we don't have, and we still need to determine. Do I have dA over dt?
Yes.
I do have it as a 2. This is a number, this is a number. Do I have the h over dt?
Yes.
Which is 1. So I'm given this information. This is definitely 10. I'm given this information that helps me determine b. So 100 equals b times h divided by 2, where h is 10. So 100 equals 10 times b over 2. Simplify both sides by 10, so b is 20. Centimeters. So 2 times 2 is 4. Minus 20 divided by 10. So that's negative 16 divided by 10. Or, yes, measurement unit? Careful. So the measurement unit is this over this. Per. Is this clear? Any questions? Any questions? So at what rate is the base of the triangle changing? So it will be decreasing. Any questions? Is this okay? Okay, very good. My pleasure. Anything else? Is there anything else we worked on? Anything else that we want to see? Anything else? Okay, we're going to have more examples because we're going to review. I'm going to bring you the previous tests and we're going to work on those problems. And when we review, we're going to go over other related rates problems, unless you have something in mind right now from related rates. Anything else from related rates? Okay, so let's take a look at 3.10. Linear approximations and differentials. This concept was discussed last time when we looked at that cost and marginal cost function. So before we look at an example and we try to understand what this means, just allow me to refresh your memory. We had a problem in which we were interested in determining the marginal cost, which was the derivative of the cost. But then we said, okay, let's see what happens to the cost if we increase the production, let's say per day, by 1 unit, not by 100 units. It's not going to work. It's too far out. But we have 200, but now we want to talk about 201. At that point, at that particular point with C of 200, C of 200, there is a tangent to the graph of C, correct? Now, if I change x slightly, that tangent is still valid. That slope of the tangent is still valid. If I go up here, it's not going to be. But 200 and 201 or 200 and 199, it's okay, right? The slope will give us the rate of change when we change x a little bit at that point. So this is the concept of differentials and closely linear approximations. So here's a function. This is f of x. Back to our point from the very first day of classes. P, of course, of x comma f of x. It's all the same so far. Of course, this is x. And of course, this is f of x. So this time, like before, I'm going to change x slightly. But I'm going to show it as if it's huge, because otherwise I can't explain if we have to look with the magnifying glass. So we're changing x slightly, but this time we're not going to call it h. We're going to call it delta x. It's the same thing. So it's delta x, also called dx. Also called h if that's what you want. It's still a minor change in x. By minor, I don't mean from 200 to 300. I really mean minor. Of course, now you're going to give me this point. So please, anyone give me the point Q? Yes. Right, obviously. Perfect. I am going to draw the tangent line at P and extend it. So this is the tangent at P. Obviously, this is f of x plus delta x. Now I want this distance. This distance is called delta y, which is the exact change in y when a change of what? Of exactly delta x in x happens, occurs. So delta y is the exact change in the value of the function, what we determined last time, c of 201 minus c of 200. This is delta y, the exact change in y when a change of delta x in x happens or occurs. So can anyone give us the formula for delta y? the exact change. So I will write when x changes by delta x, y changes and it's delta y. What is it? Can anyone dictate?
F of x plus delta x minus f of x.
So remember this was C of 201. The minor change was 1. X was 200. And this was C of 200. Remember from the formula with from the problem with the cost. Yes? Okay. Now coming back to the graph, I will extend this vertical line. And now I will create a right triangle. This is one leg, and this is the other, and this is the hypotenuse. So this is a triangle. This is a totally different distance. And you will tell me in a moment what that is. We know this distance. What is it? Perfect. Now, in this right triangle, let me take it out of there. We know that this is delta x. And we know that this line has a slope. Can anyone give us the line of that slope? Remember what that line, say it again?
Can you go back for just a second to the
So do we know what that slope is? We know what the slope is because we know how we drew that line. And what does it represent?
The derivative.
Perfect. So what is it? The slope equals?
X prime.
It cannot be x prime because the function is f. The function is not x. F prime of x, indeed. Right? At that point, right? Because it's x. So at this point x, the slope of this line must be f prime of x. Agreed?
Yeah.
But now, please tell me, I'm still trying to figure out this. I haven't figured out this piece yet. But we know that f prime of x can be rewritten somehow. We used it many times. Yes?
D
y over dx.
Of course. Of course. So stay with me for a second. Forget about the fact that this is a tangent. This line is a tangent. Can anyone give us another way of writing the slope of this line? Whatever over the opposite over, right, the rise over the run. Well, the x is the same with delta x are the same. So then for these two to be the same, what is the top?
dy.
So this is dy. So what does dy represent? No, you're right. You're on the right track. But wait 1 second. Dy is the differential of y. What is the differential determined with? Not as an exact change, but using the derivative. Exactly, which is a limit. The differential of y, in parentheses for us to remember, obtained using f prime, not f of x. So in order to determine the exact difference, I use f of x. So coming back to what we did with the cost, what was dy? You can go back to your notes, and I can go back to the lecture notes. What was dy in the problem with the cost? 32.00 blah blah. What was delta y in the cost?
32.
$32 per unit. Now you can say here, but this is a huge difference. Look at delta y and look at that dy. But just remember, this point is really here. Because the change in x is 1, not 15, as I showed it to you here, so I can talk about it. So the change in x is right here, at the most 1. Okay? So then this point is right here. Therefore, I can definitely conclude, even from the same example that we looked at, that the relationship between delta y and dy is, I cannot use equal. Exactly. Exactly. So the actual change in y, or in the function, triggered by a tiny change in x, can be determined quite accurately, not exact, but can be determined using dy. So from here, can anyone solve for us to tell us what dy equals to?
dx times
F prime of x dx. Cross multiply. So put this over 1 and cross multiply. dy, the differential of y, is f prime of x dx. So coming back here, this is a crucial relationship. So please dictate, what do I replace the left-hand side by? The left-hand side?
From y.
The left-hand side.
Oh, delta.
Delta x, or x plus delta.
Yes, this time I'm going to use dx. It's the same thing. Okay, f of x plus dx.
Plus or minus
Good.
f of x.
This is the left-hand side.
Left-hand side.
Yes, this is the left-hand side, yes.
Oh, I see.
So now the right-hand side. What is the right-hand side, please?
F prime of x.
Good. The only thing I need to do is move f of x to the other side.
Super imp.
Super imp.
Super important.
Yes.
Oh, little creature.
A big little.
Yeah, super imp.
Okay, let's talk about this one more time. So see how we got it. So here's what we did. We looked at the function, like the cost function we had. Imagine that this is 200. Imagine that this is 201. So there is a minor change in x of 1 unit. Well, obviously, the change in y, for our example from before, was 32 point blah, 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 blah. Then we created a right triangle, and we used f prime of x. But this is dx. The question is, what is this? Well, because this, the slope of this line is f prime, and is also the rise over run, then f prime must equal dy over dx. Because we know that f prime means dy over dx. Now you can say, and you can ask this question, but you never told us that those two have different meanings. You only said that f prime of x is the derivative of y with respect to x. Now all of a sudden you give a meaning to the top and you give a totally different meaning to the bottom. We never thought about that before, right? But that's what it is. So the slope of this line is f prime of x, and it can be rewritten using Leibniz notation, where dy is the differential in y, the change in y triggered by a minor change in x, and dx is the actual change in x. So let me give you an example of what we do with this, and then we look at other things. So let's say we have 1 divided by the cube root of 999. How will I determine this? Plugging it in the calculator, right? Okay. So I need to identify a few things. And what are those things? And I'm going to highlight them in red. I need to identify the function I'm talking about. I need to identify x that I'm talking about. I need to identify the x that I'm talking about. And then the rest will fall into place. So let's look at what we are asked to find. And let's identify those 3 pieces. So please tell me which function we are talking about, which x we are talking about, and which minor change we are talking about. And you can say, how could I know? But think of something that you know and make a minor change from what you know.
Would it be f of x would be the 1 over x?
Cube root x,
Okay.
How much is x?
1,000.
Exactly. And what is the minor change? Careful. -1. So let's see if this makes sense. Is this the function 1 over the cube root of x?
Yeah.
Is what I know easy, the cube root of 1,000?
Yeah.
Which is 10, correct? And obviously there is a minor deviation from 1,000. You're not going to look at 4,800, right? You're going to look at something that gives you a tiny change. This is tiny. Dx is tiny. You can go to something else, right? I know the cube root of 8. So how come that I don't use 8? Because from 8 to 999, it's 5 days away. So I have to think in terms of the minor change in x. It has to be minor. So that's how we choose 1,000 and not the cube root of 8. Okay? Good. So now all I have to do is mimic this. So we know that I have to find f prime. We know the x. We know f of x. What is f of x? F of 1,000 is 1 over 10. So I have f of 1,000. I have the x, but I need to calculate f prime. So in order to calculate f prime, first I have to find or rewrite it as x to -1/3. Because I'm not going to use the quotient rule on that. So I change 1 over the cube root of x into x to -1/3. And now I can differentiate. So f prime of x is what?
-1/3.
Perfect. Times x to which power?
-2.
So -1 over 3 minus 3 over 3.
Perfect.
Very good. Now I have to change it back into -1 over 3. So this will be the cube root of x cubed and x. So it's x, the cube root of x. It's the cube root of x to the 4th. So I took an x out. So this is the cube root of x to the 4th. 1 over, of course. So I changed it into x cubed and x. So an x is outside. Any questions? One more time, what are we trying to do? We're trying to approximate this using calculus. And then we'll see how approximate is it. Any questions so far? Please ask. You don't seem convinced. I'm sorry? Paul?
I guess I'm missing a problem here where you took an x.
So this is x to the 3rd and x. The cube root of x cubed is x, and the cube root of x is the cube root of x. Whenever the power is higher than the index, you can take the quantity out.
So it's just like you subtract the exponents, right?
I change it into 3 over 3. Yeah. Is this okay now?
You made it 1.
Yes. Exactly. So I can apply the cube root. Is this okay, everyone? Okay. So now let's put everything together. 1 over the cube root of 999 is approximately what?
110.
Very good. Then plus, well, it's going to be minus, but I want you to see what I'm doing. Negative. This, so this is 1,000, and this is the cube root of 1,000. How much is the cube root of 1,000? 10 times 1,000, 10,000 times 3 times dx. How much is dx? I don't think you would have expected this. So 1 over 10 plus 1 over 30,000. The least common denominator is 30,000. This needs a 3,000. 3,000 plus 1 is 3,001. Now let's see how close we are. I guarantee you we are very close. And we didn't even use the calculator. So 999 caret -1 divided by 3. And the other one is 3,001 divided by 30,000. Because dx is tiny. I think we need another example like this. A problem like this will be on the test and the final. So let's choose. The top of page 255, anything you want. Or we can make one up. Whatever you would like to determine. Which one? Let's look at 23. Did you choose or not yet? 1.999 to the 4th power. Here is the way I would recommend you memorize it. Yes. Oh, thank you. So here's how I remember this important relationship. Here's how I do it. The function applied to x plus a little bit is approximately the function plus a little bit of y. The function of x plus a little bit of x is approximately the function plus a little bit of y. Okay. Say it again, Paul. So I need to identify 3 things, and I'm done. Which page am I on? This was 4 or 5. No. Okay, I need 3 pieces. I need this, I need this, and I need this. The rest is history. What function are we looking at? Obviously. Which x value are we looking at? Okay. Which dx are we looking at?
-0.001.
Awesome. For this to work properly, dx has to be tiny, or as small as possible, if that's the case. And now I have to find f prime of x, which is 4x to the 3rd. I have to find f prime of 2, which will be 32. And now I can approximate 1.999 to the 4th power using calculus. What do I have to write first?
the function.
Yes, so f of 2. 16 plus f prime of 2, 32, times negative 0.001. So 16 minus 0.3 decimals, 0.032, which I know how to do. No calculator is needed. So it's 8, it's 6, it's 9, 1, 5. So my question is, would you prefer to determine delta y for the minor change, or would you prefer to calculate this to the 4th power, or do you prefer to subtract these two and get that? Would you like to erase this by hand? Let's assuming we don't have calculators. Would you like to take this to the 4th power, or do you prefer this subtraction of these two numbers?
Yeah, I'll do that one.
So that is the difference between C prime of 201, C of 201 minus C of 200 versus C prime of 201 from last problem. Okay, so what do we get?
So I just have a quick
Please.
question. So the problem, we're basically making that the left side, right?
Let me take a look.
Equation, and then we're just plugging in on the right side.
So this is the function of this. So this is this.
Yeah, so the problem is the left side.
Yes,
Okay.
yes.
Whatever we
So we are
calculate-
asked to find the function of x plus a change. It could be positive or negative. So we are asked to find a function of something we know that changes slightly. So what we know is 2, and the slight change is negative 0.001. And the right-hand side comes from here, from this very important concept, that the actual change triggered by a small change in x, the actual change in y is approximately the differential of y. But the differential of y is this piece. The actual change is this. All we did, we moved f of x to the other side to get this. Was that the question?
Yeah.
So we have this, and let's see what we get. So 968, and we got 968. Without trying to determine that. Of course, it's not exact. It's not perfect. But this is very elegant, and it's a very good result. Okay, so let's look at, do we need more, or do we need a trig function, or can we continue without the time? Okay, very good. So let's say, I don't know, tangent 44 degrees. No one can determine this by hand. I know, I hope you agree with me. No one can determine this by hand. So let me caution you on something. We do not use degrees in this class. We have to use radians. It doesn't matter. You'll see in a moment. Okay, so just remember, never ever have your calculator unless we have tangent of 44 degrees, but it's not 1 degree anywhere, but applied a tangent or a trig function is applied to it. Okay, so I know that this is approximately f of x plus f prime of x dx. So we can approximate it. So I need to determine, so this is the same with f of x plus a little bit. I need to determine this, I need to determine this, and I need to determine this. And then I can put them in. Which function are we talking about? Very good. What is its derivative? Because I need it here. Good. What is x? Something I definitely know.
45.
Perfect. And what is dx?
1. Or -1.
Negative 1 degree. Perfect. So then tangent 44 degrees is approximately, you don't have to give me numbers yet, just tell me what to write.
Can we do the,
So it's tan 45 degrees.
Very good. Tangent 45 degrees. We'll write plus, but that's okay. F prime of 45 degrees will be secant squared of 45 degrees times -1, but this must be changed into radians. And the relationship is 1 radian is, or if you would like to remember it a bit better, pi equals 180 degrees. So then 1 radian, we divide both sides by to get 1, not 3.14 radians, but 1 radian. I have to do what? Exactly. So 180 divided by pi. So I have to multiply by 180 divided by pi. Only because I need to change 1 degree into radians.
why are we changing it to everything else in degrees?
Because when I apply tangent to pi or to degrees, it's not going to change anything. But when it's alone by itself, I cannot have 1 degree. Inside the function, tangent pi over 4 or tangent 45 is the same thing. But if it's outside of the trig function, I cannot have 1 degree in anything, anywhere.
So that 180 over pi is just transferring a.
-1 degree into radians. Exactly. This piece represents 1 degree, -1 degree in radians. Exactly. Tangent 45. It's a very nice number. So tangent 44 degrees is approximately, how much is tangent 45? It's the only angle for which sine and cosine have the same value. 1. Now secant squared of 45. Remember secant of 45 degrees is 1 over cosine 45 degrees. So if you don't remember secant, then you will remember cosine. It's the only angle that has the same sine and cosine. Square root of 2 over 2. So then this will be 2 over the square root of 2, because this is the square root of 2 over 2, and now I have to rationalize. These two go away, so it's the square root of 2. But plus, well, it's going to be minus, but that's okay. But plus, I need to square this. 2. 2 times -180 over pi. So this is the same with 1 minus 360 over pi. Now you can say, well, you cannot really divide by pi. You still have to use a calculator for this. I will have to agree. Because I can, but it would take a while. So let's go and go to mode, because we chose 44 degrees, and change it to degrees for a moment. And go to tangent, 44 degrees, see what it is, and then 1 minus 360 divided by pi. Nobody looks?
Oh.
No, I did something. I have to go back and look. What did I do? So tangent, let's take a look.
dx is y in degree.
Right, I reversed this. Sorry. So 1 degree into radians, not 1 radian into degrees. So sorry about that. So let's change that. It's pi over 180. Makes no sense. Sorry about that. I got carried away. No excuse. Yes, 1 radian is correct. It's 180 over pi, but we want 1 degree. We don't want 1 radian. So we want 1 degree, which is pi over 180. Yes, that's what we want. So I have to change that. Sorry. That's how we know we have an error. I should say I have an error. Okay, so let's change. I have to let it dry for a second. So I have to write pi over 180. So 1 minus 2 pi over 180. Or you can simplify, pi over 90. That's even better. So this is 1 minus pi over 90. And I'm going to erase this all together. And they have to be very close. Let's take a look now. So 1 minus pi divided by 90.
You got 0.97 from that.
So the tangent 44 is 0.965688, and what we calculate is 0.9650. 3 decimal digits. Quite good.
How'd you get pi over 90? I guess 2.
So this is,
Plus 1 minus 2.
yeah, so this is the 2.
You have to change over.
Oh. So this is pi over 180. So this is pi over 180. Simplify by 2. You get 1 minus pi over 90. And this is 0.96509. Okay, any questions? Yes, please.
Or would it be